Hi, this is Olympiad geometry. Let's continue our study of the Ceva theorem. AB is diameter of circle O. Chord CD is perpendicular AB on point L. M and N are on LB and LA, and LM to MB equals to LN to NA. CN intersect circle O on point E and F. Proof: AE, BF, OD are concurrent. So when we have this problem, we look at, we want to prove that the three lines are concurrent. So we know that we want to use Ceva theorem here. But how can we use the Ceva theorem? We need to either find a triangle and three lines of this triangle and find the ratio relationship with the segment, or we can use the angle form of the Ceva theorem, which we haven't tried yet in the previous videos. But why we want to use the angle form of the Ceva theorem in this problem? Because if you look at the figure, it's a circle. So there are a lot of angle equality on a circle due to the same chord or same arc. That means we can at least try this direction. So let's just connect AD, connect BD. Right? We want to prove AE, BF, OD are concurrent. That means we need to find the relation between A, O, B, and B to this point to D, and D to this point to A, right? But if you look at this figure, the segment length of this to this is very difficult to find. Why? Because we have no information on how to generate this point, right? The only information is that we got a ratio LM to MB equals to LN to NA, which is very difficult to relate back to this line, right? LM to MB ratio to this ratio, it's very difficult to transfer it. But if we think about the angle form of the Ceva theorem in triangle ADB, right? So let's try it. Actually, it's because we are trying to prove AE, BF, OD are concurrent. It's a converse theorem of the angle form of Ceva theorem, right? So we just write the equation down and we try to prove it. So use angle form of Ceva theorem, which means that we want to prove sine angle. Let's start from point A, right? So ADO divided by sine angle ODB. So we on the triangle ADB, right? We want to use this on triangle ADB because we are trying to prove these three lines. So we need to find, from these three lines, we need to find 3 points as the vertex of the triangle. So here it's kind of obvious that we want to use ADB as a triangle rather than OEF, right? That's more difficult. So we can try this. We want to use the angle form, that's sine ADO to sine ODB times, because we start from B, point B, that's sine angle BAE to sine angle EAD times sine angle DBF to sine angle FBA equals to 1. We want to prove this. Now we look at the angle. That's angle ADO, and angle ODB. We know that AB is a diameter, so AO equals to OD, which means the angle ADO equals to angle OAD, right? And because CD is a chord that's perpendicular with the diameter AB, so the bottom half of the triangle that's like ADB is actually congruent with the triangle on the upper side of the ACB, which means that we can transfer the angle ADO to the angle OAD, and eventually it equals to the angle OAC. Right, so we have a lot of angle equality here. For the ODB, it equals to OBD, it also equals to OBC. Now, let's just pending here. We look at the condition we have. We have a condition that LM divided by MB equals to LN divided by NA. Let's transfer this condition to the angle form. So LM divided by MB. So this equation, actually, we can reform it as LM divided by MB times NA divided by LN equals to 1. Right? This is a good sign because we want to prove something, some product is 1, and we have a production as 1. So we just want to find a way that we can show the equality of these two equations. Let's find LM divided by MB, rewrite it as an angle form. So LM divided by MB, that equals to the area of triangle LCM divided by the triangle area MCB. It equals to half times LC times CM times sine angle LCM, right? Divided by half times MC times CB times sine angle MCB. So half cancels, CM cancels MC, so it equals to LC divided by CB times sine angle LCM divided by sine angle MCB. We want to find LCM, right? But if we look at this one, LCM is actually angle DCE. So because DCE equals to DAE, so the sine angle LCM actually can be rewritten as a sine angle DAE, right? So sine angle DAE, and MCB, angle MCB can be rewritten as angle EAB, right? So sine angle EAB. LC divided by CB. LC divided by CB, that's sine angle ABC. check this. We have the ratio of sine angle DAE to the sine angle EAB, right? So we have this term here. That's a sine angle DAE to the sine angle EAB, the same term here. And we want to find the sine angle ABC. As we know that sine angle ABC, because angle ABC equals to the angle ABD equals to the angle BDO, right? So we can rewrite this as a sine angle BDO times the sine angle DAE times the sine angle EAB. Now we look at this. We have BDO, which is here. We have this term, which is flipped here. That means we are on the right path. We just need to find the ln divided, here actually NA divided by ln, right? NA divided by ln equals to the triangle area ACN divided by the triangle area NCL equals to half times AC times CN times sine angle ACN divided by half times CN times CL times sine angle NCL. It equals to AC divided by CL times sine angle ACN divided by sine angle NCL, right? AC divided by CL, AC divided by CL, that's 1 over sine angle BAC, right? So that's 1 over sine angle BAC times angle ACN, right? That's an angle for the arc AF, so it equals to the angle ABF. Sine angle ABF divided by sine angle NCL. NCL, that's for the arc FD, so it equals to the angle FBD. Look at here. We have ABF, FBA, FBD, FBD here, right? DBF, that's same to FBD, and we have BAC on the bottom. So here should be on the, here on the denominator. Here should be on the numerator, which we just need to check whether BAC equals to ADO, right? BAC, that's this angle. This angle equals to this angle, BAD, which is OAD. OAD equals to angle ODA. ODA, right? ADO. That's the same thing. Which means from LM to MB times NA divided by LN equals to 1, we can rewrite it as these two terms. That's a sine angle ABC to sine angle, this one, BAC times sine angle DAE to the sine angle EAB times right, this one and this one, sine angle ABF to sine angle FBD. Right, we just need to flip it. So once we flip it and we find that this term equals to this term equals to this term, and this term equals to this term, we got this one. So I'm not going to write it. We got this one equals to 1, and we use a converse. We use a converse Ceva theorem in angle form. We know that AE, BF, OD are concurrent. Now we think twice of this problem. We start from looking at how we're gonna use the Ceva theorem to prove the three lines are concurrent. We can choose to use the angle form or use a segment ratio form, which is linear form. But the linear form is very difficult to use because we have no relation or no condition tells us about the relation of this ratio, segment ratio, right? We have no information on that. Thus, we can, and also because it's in a circle. In a circle, there are lots of angle equality, so we can try to transfer some angle ratio to another form. In that thought, we try to we connect the AD and BD, and we try to write the angle form of the triangle ADB. And then we transfer the condition ratio to a production, which is similar to what we want to have. Then we rewritten this equation in angle form, and then we find that this angle form actually matched to what we want to prove. Then we got the whole proof. I hope you like this video. We will talk more about Ceva theorem in next videos. Thank you for watching. See you in next one.